press that one.
Oh, no, not yet.
It is already being done.
No, we just started live streaming.
I think we're live. Can someone confirm that maybe?
I cannot see it yet.
Okay.
Well, let's wait a second.
Yeah. It's live. John says it's live. So I think we're live. Okay. Welcome everyone to another Safari live seminar. This live seminar we have Behzad Salami presenting his work. Behzad is currently working with the Safari Research Group, and prior to that, he received his PhD from UPC in 2018 and did a postdoc at Barcelona Supercomputing Center following his PhD. And during his career, he received many awards and grants, and his research interests are reconfigurable computing, low power and fault-tolerant accelerators, and near data processing systems. And today he will talk about the projects he worked on during his during the later half of his PhD and spanning his postdoc journey. So Behzad, would you like to start?
Yeah, thanks, Atabak, and thank you very much for the introduction. Actually, that was correctly mentioned that this work is a part of my PhD as well as my postdoc that I have been working on. And actually, currently also I have a couple of ongoing work related around to this project actually. So I'm very excited actually to present this work today, both for the attendees in the Zoom, the Safari Research Group, as well as the YouTube attendees, also people who are watching this video in offline. So I'll be happy to get any feedback, comments, questions that you may have online or offline from both media. So yeah, I will talk about the title, as you can see, understanding the reliability and power efficiency trade-off of modern FPGAs through undervolting. So there are a couple of keywords here, as you can imagine. So I would like to mention them before going through the slides. So we have one of the most important keywords probably is undervolting, which from our terminology means supply voltage underscaling below the safe level that is set by the manufacturers. So we have FPGA as well. So as you know, most probably I think everybody is familiar with that. So they're kind of computing processing systems which somehow provide very good efficiency, parallelism, data flow programming, architecture, and also reconfigurability. So we have proposed this technique, which it is a very good, efficient technique for power saving for FPGAs, and also we have studied how this may impact actually the reliability and power efficiency. So clearly there are other parameters that could be affected through this supply voltage underscaling, but these are, I think, the most important parameters that could be studied. So they are kind of trade-off with all of them, with these two parameters. So I'll be gonna talk about more details around this topic. So please feel free to ask any question or comment that you may have anytime during my slides. I will be happy to answer them as much as I can. So let's go through the slides. So here's a quick executive summary of what we are gonna talk today about. So as a very high-level motivation, power efficiency, as you can imagine, is actually very important. Let's say parameter compared to previous decades, I would say, which was more efficiency and performance. So now we are talking about power efficiency, and which it is very important because of the size of the data, which it is growing a lot. So we need some techniques which can actually optimize this power efficiency for the underlying hardware as well as for the application level, and actually at any levels of the computing stack, basically. So of course, general purpose processors are not very efficient for this because they are not really fundamentally designed for power efficiency. So we have hardware accelerators, and among them FPGAs are a very good one actually. Well, I mean, that's a good one. I mean, that they can provide flexibility, which is very similar to, it's a kind of similar to general purpose processors and GPUs as well. And also they provide a lot of efficiency, throughput, performance, I mean, compared, which it is comparable with the application specific devices like ASICs. However, when we really compare FPGAs with their equivalent application specific devices, they are not that much power efficient. And I think the reason, the most important reason is that because in FPGA, we add a lot of components to provide flexibility for the device, like SRAM, for example. In the typical FPGAs that we have a lot of configuration bits which are SRAM, and they're consuming a lot of power. Or we have routing switch which provide a lot of which consume a lot of power consumption. So we have FPGAs which are good in terms of when they're compared with processors and GPUs, but they are not really good when they are compared with the ASICs. So we have a gap. We have a power efficiency gap, which it is quite huge. Is at least 10 times we have power efficiency gap. That depends a lot with the device, what kind of comparison we have. But this is like a typical number, which just to make sense how much efficiency, how much gap we are talking about. So the power efficiency gap is something really important, especially considering that FPGAs is going to be even more important than I would say the before. We have now a lot of data centers that they are using FPGAs. We have a lot of embedded systems that they prefer to use FPGAs, again, because of their unique features, which I will later talk about that very briefly as a background, let's say. So to bridge these gaps, so in this work, what I have been working, it was exploring the supply voltage underscaling, because we have, so you know that the voltage, supply voltage is actually very important parameters for power. It's driving everything. Without power, nothing works actually. We have zero power, but without voltage, actually nothing works. So we have voltage set to the device, whatever device it is. It can be a memory, it can be a computing unit. So we have FPGA which has a lot of components. So we push the devices to work or to operate under the default voltage that is set by the manufacturer. So, and we explored how it impacts the power efficiency, which it is our main goal, but it has some disadvantages, some overheads. These overheads can be performance overhead, or it can be reliability overhead, and things like that, which we will discuss later actually. So as an evaluation setup, we have studied several topics, let's say subtopics, I would say, which includes voltage margin characterization. So it is a kind of margin that is set by manufacturers to make sure that the device will work under worst case conditions actually. So we have studied how much power efficiency we have, how much reliability overhead we may have. We have proposed a few error mitigation techniques which can enable actually to taking more benefit from undervolting, because without significant, let's say, error overhead. So we have also studied frequency underscaling, and also a couple of other things that I will discuss later during the talk. So we have studied several components of FPGAs. As you know, FPGAs are quite heterogeneous devices. They have many different type of subcomponents inside them, just to make sure that this is like a heterogeneous system and can do many type of computation. So we have applied it for computing units like lookup tables, for SRAM-based devices, for SRAM-based components like block RAMs, and also for DRAM-based components, which is specifically was high bandwidth memories, HBMs. And as a case study application, so we have looked into machine learning applications for a few reasons, basically. So the most important reason is that, of course, it is very popular. It's getting more and more used in many different domains. So it is very important that to make sure that it is implemented very efficiently into the underlying hardware. Also, the other reason for choosing machine learning is that machine learning devices have machine learning systems, actually, including convolutional neural networks specifically. They have an inherent resilience against the error. So this means that the errors somehow are automatically covered during the computation layers of the convolution. So this is a very good observation that we have discussed this in one of our papers. So this is a very good observation because it can enable to taking even more advantage from undervolting. So as I mentioned, one of the costs of undervolting is the reliability, and machine learning systems are already somehow actually they are resilient to this error. So this means that we can push the device to work even lower voltage levels without much actually affecting the accuracy of the system, accuracy of the device. Of the application, I mean machine learning application. So among the main results that we have applied this, we achieved a lot of power saving because we saw that there's a very large voltage guard band, voltage margin below the nominal level. So this gives us more than 3 times power saving. And also even below this voltage guard band, we could save even more power. It depends, actually, this just depends on the machine learning workload because there is a kind of application variation over there. So we saved even more power below that, but with the cost of accuracy loss, which I will discuss it later. And that was quite actually impressive because this is happening without too much modification in the hardware or software. So this is a not without much overhead, basically. This power saving cost coming without much overhead. So this is more or less executive summaries that I would like to discuss today in the seminar, and we are going to look into more details. So I will start with the background just to make sure that we are on the same page. Later on, I will discuss more about the different components of the FPGA that we have applied undervolting, including, as I mentioned, internal components like lookup tables, SRAMs, IBM memories, and at the end, I will be happy to discuss the open problems, the issues that we have observed during this study, and also the potential research topics for the future and also ongoing works. So let's start with a quick background with this. So since we have mainly target machine learning application in this work, I would like to have this slide here just to discuss a bit about the optimal hardware which it is possible for AI applications, including convolutional neural network, for example. So we have many new requirements for the hardware which is supposed to run AI applications. So this list can be very huge, but I think most important of them are power efficiency, latency, heterogeneity, flexibility, and also data movement, and etc. So where are FPGAs here? Actually, FPGAs, they somehow could provide some kind of trade-off between the devices, application-specific devices, which are kind of specially designed hardware for that machine learning, so they cannot do any other things. So they are pretty specialized and customized and very efficient for that. So they have very high efficiency. On the other side, we have very good flexibility for general purpose processors, but of course they are pretty flexible, and also they are not much optimized. FPGAs sit something between, actually. FPGA, they provide, from one side, they provide flexibility. Also, they have lower latency compared to CPUs. They provide a lot of parallelism. If we could somehow exploit this parallelism, that would lead to a lot of efficiency, actually. But so the machine learning, actually, this could be a very good potential, because in machine learning, we have a lot of parallel computation, which means that with a very nice implementation, this can lead to very good parallelism. So on the other side, we have some disadvantages, of course. So their programming is not that easy compared to processors. So we still need a bit of, let's say, I would say, hardware and software knowledge for a programmer to be able to program FPGA very efficiently. However, this is actually there's a lot of research behind this, including like high-level synthesized tools. They provide high-level tools which can easily program FPGAs, but of course there's a lot of optimizations which can be, I believe, that can be applied into that. So we have complexity. So they are so as I mentioned, most of the disadvantages actually comes from the programmability, lack of the library, also runtime optimizations, etc. Which means that implementing a really efficient application like machine learning into such devices could be a bit costly in terms of the human cost, basically. But rather than that, I think that they are completely, let's say, they could be very efficient compared to general purpose processors. However, the other disadvantage I didn't mention, I think that is not listed here, is the power efficiency compared to ASICs. So actually, this is the both advantage and disadvantage compared to where, depending on what we compare to them, we compare them with what kind of devices. If we compare them with CPU, so they have very good efficiency, but if we compare them with ASICs, they do not really have good efficiency. So this is the point that actually that we are going to improve through this form. So beside that, so FPGAs are getting even more popular, not only for machine learning, so they are getting for many domains, as listed some of them here. So this is just to show that FPGAs are getting much more popular, and I have seen actually a report that in I think these days in more than 30% of the data centers somehow FPGAs are used, so are being used. I mean, so this number actually is very huge, because typically data centers, as well as this embedded systems that you can see here listed here, so we usually use the CPUs or GPUs, but FPGA are getting more popular because of their advantages that I discussed in the previous slide. So we have these devices which are important. I mentioned about the power efficiency gap that we have between FPGAs and ASIC. This report, I think it's from Intel, that shows that at least we have 10 times the less power efficiency for FPGAs compared to the ASICs. So, so what we are proposing here, what we have explored in this work, and I'm going to talk about a bit more detail about that, is supply voltage underscaling, as I mentioned. So this is a parameter that can affect both dynamic supply voltage as dynamic power consumption, as well as the static power consumption, with the different coefficients, of course. So when we reduce the voltage, actually, so both dynamic and static power are reduced with different coefficients. So this leads to directly to a power efficiency improvement. So we have we directly can reduce the power. But what's happening is that we are increasing the circuit delay of the delay of the underlying circuit, whatever it is. It can be a memory or it can be a computing unit. So this means that if we run the same devices with reduced voltage but with the same frequency, so we may have some reliability problems. So reliability problems could be exposed as like bit errors in the memory, for example, like 0 to 1 bit flip or 1 to 0 bit flip, or it can be like a glitch in the data path, or it can be like a transient or kind of permanent, let's say, bit flip or other glitch in the data path. So we have this kind of cost. Of course, we can reduce the frequency, but this may lead to, this may cause performance degradation. So this is a kind of trade-off. So we have a kind of trade-off. So if we reduce power, reduce voltage, we will achieve more power saving, but at the same time, we will lose some reliability standards of that application. So that there should be some kind of optimal point, I would say, but this optimal point is a function of a lot of parameters, a lot of other parameters, which I'm going to talk about them actually. So we have an optimal point of voltage, which power is optimized, but the reliability is not much affected. But where is this power? Where is this optimal point? It can be dependent on many parameters, which next I will be talking about them. But before that, let's take a bit detail into the architecture of FPGAs, just again to make sure that we are talking about, we are on the same page. So FPGA, typically, this cartoon shows how they are. So they have a lot of parallel components, many different type of components. So including on-chip memory like SRAMs, DSP units, lookup tables, and many other things, basically. Actually, these days FPGAs are even more heterogeneous than this. They have like soft processors and many other components. So the key advantages of the FPGAs is that they are reconfigurable. So all these components that you see here, they can be reconfigured actually. And this is their key point. This is their key advantage. And as you can see, they are massively parallel. So we have a huge number of them. They are fabricated. They are floor planned on the FPGA. So this means that if a designer or if a programmer somehow could exploit this parallelism, this can lead to a lot of efficiency for that application. And also, as I mentioned, they have quite heterogeneous components, which is clearly shown here. We have a different type of components. But in a bit more modern, let's say, architecture, which it is introduced like a few years ago, like 2 years ago, I think, or 1 year ago, is how FPGAs are connected to the DRAM DRAM chips, so very huge amount of the chips. So traditionally, FPGAs were connected through off-chip memory, so we have like off-chip connection between them. But this off-chip communication is costly a lot, so it consumes a lot of energy, and also especially for those applications that requires a lot of data movement between computing unit and the memory. So the off-chip communication can be costly a lot. So this was traditional, but in a bit more modern architecture, as you can see here, so we have silicon interposers, which somehow enable connecting FPGA to the layers, the different layers of the to an stack of FPGA, stack of memory on the same package. So the connection is not actually off chip. It's not on the same die, but it's in the same package, which is still fine because it doesn't. It provides a lot of the high bandwidth. So compared to traditional communication, which bandwidth was quite limited. So here we have a huge bandwidth, which it is good for especially, as I mentioned, for those data intensive applications. So this is also one of the FPGAs. So in our study, we somehow looked into the efficiency of the FPGA undervolting for both type of the typical as well as the modern devices. So which I will talk in the next parts of the presentation. So and our study includes 3 major components. At the moment that I'm talking about, which it is first lookup tables, which they are kind of actually computing components, but they can be programmed as memory as well, but they are mostly used as a computation unit. So we have SRAM based on-chip memory. So these are they call usually block RAM, so blocks of the SRAMs, let's say. And also we looked into the DRAM chips, stacks of the DRAM. So for these 3 parameters, we have explored the effect, the power efficiency gain of the undervolting, as well as the reliability issues that it may have. So before going to the details of the results, numbers, discuss the things, so I would like to, let's say, show a very high level of the behavior that we observed, so which it is actually kind of common for all the 3 components that so far we looked into. This is important because the next part of this presentation will be actually detail of this. So it is good to see here. So this slide here, I think. So we observed that there are like 3 voltage region or voltage area, let's say. So at the first one, we have a supply voltage which is set by the manufacturer. We call them via let me see. We call them via nominal voltage level. This is the voltage that manufacturers set on their devices, and what we observe is that this voltage level is quite conservative for the device and also for the application that is running on the device. So what does it mean? So this means that if you reduce this voltage until some points, until this threshold, we do not lose any kind of reliability or performance and nothing actually. So this means that this is a kind of margin, which actually is very huge margin in most of the devices that we have experimented. So we call them guard band area or margin area. So in this area, we have no performance or reliability loss. And we believe that this is intentionally set by the manufacturers because they are thinking that the device might be used in many harsh environments. I know, low or high temperature, or it can be a lot of radiation in the environment, or this things like that, or maybe the other things that they have thought is that so we have process variation, so we do not have like a ideal process fabrication process. I mean, so during this fabrication process, so we may have some chips which requires higher voltage level than the minimum level that they can really operate. So for this kind of reasons, we believe that so they have set a very high voltage level, but of course which it is fine. So this means that their device can work under worst case conditions. But the problem is that this adds a lot of unnecessary power consumption to the device. And considering that the power consumption is a very important actually metric these days, so this is not this is not accepted actually, because this is not probably not optimal, because we are losing a lot of unnecessary power consumption here. So this is the first area. Below, until another threshold, which we call it min, meaning minimum safe voltage area. So this is the point that we have observed that the reliability of the device, of the underlying hardware, which as I mentioned, it can be lookup table, SRAMs, or HBM. The reliability of the underlying hardware starts to lose, actually. It starts to somehow collapsing, basically. It is not linear, actually. So it starts collapsing, the reliability. So this is happening for all memory type of the hardwares, like SRAM and HBM. So meaning that we have a lot of bit errors here, or so if we have an application like machine learning, so we lose a lot of accuracy here. So this continues until some point that the device stops operating. So we do not receive any kind of response from the device. This is something actually happening in most of the devices, but again, as I mentioned, this is the point that it depends on the device, it depends on the application. So there's a kind of variation here also in at which point the device stops operating. So we have this kind of three area. And of course, as I mentioned, this is the behavior of the reliability of the system, because initially, as I discussed, that we are going to study these two parameters. Power consumption, power efficiency actually constantly improving from the nominal level that we start undervolting until the point that systems start crashing. But the reliability also, as I mentioned, start to degradation, start to collapsing from the minimum safe voltage area from this point. So this is more or less the general, I would say, the behavior of the voltage that we observe for the several components of the FPGA. In the next sections, I will talk about, I will elaborate actually this more for these three components. I will discuss a lot about the reliability and power efficiency that we may have, how we can actually protect the device to not to have that much reliability issues, and we can constantly continue the power efficiency gain. So we will talk about this in more numbers and also with more components and with more details in the next three parts. So this is, as I mentioned, similar behavior for all the FPGA components. So next I will talk about, as I mentioned, more details, but I think that here is a good time to take any questions about the background that I proposed, that I discussed here. If you have any comment or question, please feel free to ask.
So Behzad, I don't see any questions on YouTube.
Okay.
Also, well, I don't have any questions, but maybe we can ask
Okay.
the Zoom audience. Have any? I guess they don't. So maybe you can continue.
Okay, cool. Yeah, hopefully everything is clear actually. So next I will be talking about these three components, FPGA internal components, especially lookup tables. So I have discussed that we have tested it for convolutional neural networks, which it is, we have here I showed how it is implemented. So we have this implementation here. So you're familiar, hopefully, with the convolutional neural networks, which are very common type of the AI systems. So they are set of layers, different type of layers, convolution, pooling, hidden layers, etc. So we have this implementation on the FPGA, which applied some kind of optimizations on the application layer, like quantization and pruning. Also, we have exploited the block RAMs for storing the weights of the neural network in the inference layer, in the inference stage. I mean, this is not the training actually. So also for the computation, we have exploited DSPs as the MAC unit. We multiply and add computation unit, which are the fundamental computation unit for the machine learning application. And what we did actually here is a hardware layer voltage underscaling, as you can see here. So we have usually on the devices that we have looked into, there's a kind of off-chip voltage regulator, which is controlling the supply voltage of the different components of, somehow controlling the supply voltage, feeding the supply voltage of the different components of the devices. This is controllable through some standards. Power management bus is the most typical one. And this is pretty accessible through the processor on the device, on the FPGA, I mean, or through off-chip processor as well. So we have this kind of setup here. So we have tested several workloads, the most typical workload of the image classification workloads from the convolutional neural networks, because it's very important to study, I think, the workload dependency, the results that we have observed, it could be a bit dependent on the workload, actually. So I mentioned that we have applied quantization and pruning because, as well, I'm not going to go to detail of these techniques, but they're typical implementation because in a default implementation, so in a typical image classification workflow, we have a lot of data which are actually kind of zero or near zero. This data is just overhead because they do not contribute in the final final result, let's say, final outcome of the application, but they require computation. So quantization pruning is a kind of eliminating those kind of zero computation, which is a lot actually. So just to give an example, so for pruning, it has been shown that in other works that even more than 70% of the pruning would be okay for some kind of workflows. So we have applied those techniques because they are very important and they help to even achieve more power saving. So in this part of the study, which it is the internal component, is based on Zinc Ultrascale Plus from Xilinx, as you can see here. And we looked into this device actually is fabricated, if I remember correctly, in 20 nanometers, I think, if I'm not wrong. And we looked into the internal voltage, which is called VCC in. So there's a several volt supply voltage levels here. I know I don't remember correctly, but for this device, it should be like 15, 16, something like that. So one of them is feeding the lookup tables, routing resources, etc. In this part, we have looked into that part. The nominal voltage level that is set for this part is 850 millivolt. This is something set by the manufacturer. But as I mentioned, through this setup, we can change it, basically. We can regulate it. We can downscale it. So this is what we have done. And this is the very high-level results that we have observed in terms of the power and also reliability. Let's look at the power first. So, which it is shown here in terms of the power efficiency, meaning giga operation per watt, for several workloads that I mentioned, and also for different voltages, starting from 850, which it is the nominal voltage, goes until this point, which it is the point that the device crashes. And we have, as I mentioned, we have the minimum supply, minimum safe voltage, VMIN, which is the point that the reliability of the application starts for collapsing. So meaning that all this green area that you can see here, we did not see any accuracy loss. So this application, they are defined based on accuracy. So we have set our image and we classify them, and we see that with this accuracy, for example, for this workload, for this inception, it is called. So the default accuracy is around 70%. So until this point, we do not see any accuracy loss, meaning that either there is no error because of the voltage margin set by manufacturer, or the error is somehow covered by the machine learning. So what does it mean? This means that we have variation across applications, and also the machine learning can somehow. Sorry, I think it's jumping automatically. So also we have, so the application can somehow cover some of the errors, basically. So we achieved a lot of power saving, more than 3 times. So averagely 2.6 of it is without any cost, but we have some cost for the rest of that, which is the reliability cost, as is shown here. Also, the reliability is discussed here. There's a kind of variation, as I mentioned, for the different workload, as you see here. So we have several. We have tested also. I forgot to mention actually that we have tested several identical devices because the process variation of the device is also very important. So if you compare the same chart, different diagrams, it shows the device variability. And if you compare the different charts, actually, it is the workload variability, basically. And as you can see, we have variation, which it is not actually little. We have significant variation. So we have this minimum safe voltage device variation for this certain workload. And also for the other workloads. Some of them, they crash earlier, like this one, and some of them, they crash a bit later, actually. And also, so we have this, and also for this one, so we have, for example, for AlexNet, we have the accuracy loss is until 50% because our class number is just 2, but here we have almost 0. So at the worst cases, it works like a random classifier, let's say. So what is the message at the end of this slide is that so the very high level power saving is more than 3 times. A big part of it is without any cost. In the room conditions that we have tested all these devices, if we could test the other environment, this number could be different actually. But and also we have some additional power saving, but this is with cost. And how much of this cost? This cost depends a lot on the workload and also on the device. But what is common between them? The common thing is that we have a accuracy collapse, basically. So we have accuracy which is collapsing from the nominal level into actually the minimum possible. So into the point that the classifier operates like a random classifier, basically. So this behavior is shown here, and as you can see, this drop for all of the workload is not linear. It is quite harsh, actually. Accuracy loss, and I will discuss later why this is happening, because the number of the errors and the rate of the errors that we have seen is that is actually is not growing linearly through undervolting. It is growing very fast and very suddenly, basically. So we have this behavior. Next, I will be talking about how we can actually control this kind of cost. So we can somehow prevent device that we will not observe this kind of cost, because it's a very huge cost, and nobody, of course, wants to have a classifier which is working very bad, because this is like working, as I mentioned, as a random classifier, which is not really good. So next, one of the very
Behzad, sorry.
Yeah.
I wanted to ask you something.
Yeah, of course. Go
so
ahead.
You've replicated the well, you have used 3 platforms in these experiments.
Yes.
And
yes.
those are the same FPGA boards and same model FPGA boards, different FPGA boards, right?
Yes, exactly.
And you saw some like variance due to, I guess, process variation.
Yes.
So do you think this would generalize across different generations of FPGAs, or different even maybe processing technologies? Like if the same thing we were to do in ASIC, for example, instead of FPGAs, would we observe similar behavior? Do you think it generalizes?
Well, yeah, thanks. That's a very good question, actually. Just one point before answering the question directly is that, so this behavior, this variation that we observed might be because of the process variation, but there are other things that could have effect, like aging, for example, because we have this FPGAs not exactly, I mean, not with the same age. They had different age, basically. So one of them we just bought it in that day. One of them it was used for 5 years or something like that. So it could be different things than process variation. But process variation, most probably, it is one of the most important parameters that is causing this kind of variations. So, and actually that is a good point, because one of the things that we have done, it was testing different devices. And we have observed very similar behavior, but which I will talk next in the next parts of this presentation, which is based on a different type of devices. Because that studies, which I will talk later, it was earlier, and the generation that we had, it was earlier generation. So we had like, they were fabricated in 28 nanometers. These devices that I'm showing, this slide is fabricated in 20 nanometers. But we have tested some devices fabricated in 28 nanometers, for example, and they are a bit older generation, basically. But of course, yes, you are completely right. 3 is not a big number for such statistical studies. But it's a bit hard to be honest, it's a bit hard to get access to FPGAs. Because yeah, we have data centers, but most of the data centers are based on CPUs and GPUs, but it's a bit difficult to access a lot of number of FPGAs. But yeah, you are completely right. It is nice to have 300 than 3. But what I personally, let's say, guess is that this behavior is kind of common, because as I mentioned, we have tested totally around 10 FPGA, same behavior observed for all of them, from different generations, from different ages, let's say, and from at least for the same vendor for the same manufacturer that we have tested, it is going to be more the same, because manufacturer usually doesn't really want to apply like a huge change for different generation for this kind of settings, basically. So my guess is that it is generalizable, but it needs to be shown through some experiments, which is not, we have not done it for more than 3, specifically for this part, because it's a bit difficult to access for devices. For example, this device that we have tested, the Underscaling Plus, it was just it was not a data center device. If we could access to a data center with like hundreds of this kind of devices, that is going to be like a very good actually study. But we need to do it, and this is probably one of the things that needs to be done in the future, I think.
Yeah, that makes a lot of sense. So did you also maybe in line of like this generalization direction? So did you identify a root cause, maybe multiple root like causes, and then maybe in the low level, transistor level effect that undervolting cause, and then like these faults appear?
Yeah.
If you've done that, can you maybe elaborate on that side a bit?
Yeah, that's a good question actually. So this study that we have done, it's a bit system level study. So this means that this characterizes the device behavior, but in a let's say so studying these things in a bit lower layer, let's say in a transistor layer or a bit architectural layer. So this requires a bit of I would say having more knowledge about the devices, let's say, because so we know a bit high level information. We have a bit high level information about what kind of, for example, how is the architecture of the lookup tables for in this study or routing resources. But for transistor level study, we need to have a bit more detail about how is the layout, let's say, of the underlying hardware. So so we have not done that study to at least to confirm these results, but I think that by sharing some information with this let's say manufacturers, which it is a bit hard, I think, it is possible to do that kind of studies. But no, we at this point that I'm talking, we have not done such simulation levels or even real levels, but it is possible to make some kind of assumptions and do some simulation levels study. That is, I think that is possible. So we can assume some general, let's say, settings, general layout for SRAM, let's say, or lookup table, and apply some voltage underscaling on simulation level, and to see, for example, if it confirms this kind of results or not. This is possible to do, but we have not done it. And I think that that's also actually one of the things that I would be happy to discuss in the potential research directions. That is kind of the last part of this talks. That could be one of them actually. Thanks for asking earlier.
Yeah, Thank you for your answer. I think it could be complementary to this well, experimental analysis you have. If you had like an explanation, for example, to back that up at the circuit level, then you could perhaps easily argue, or more easily argue, that this behavior is going to be common across all silicon even devices, right? Maybe.
Yeah,
It
completely true.
seems exciting. It seems like an exciting topic to maybe follow up.
Yeah, exactly.
Uh,
I agree with
yeah.
that. Yeah.
So on Zoom chat, we have a question related to this. I'm not sure if I'm going to be able to ask it correctly, but Ismail says, could these accuracy variations be coming from different FPGA placements and routings, not only process variation? I guess if you, yeah.
That's a very good question, actually. And these results that I'm showing here are based on exactly the same bit stream. So we do not generate different bit stream for different FPGAs. So the placement and routing is exactly the same for all these results that are presented here. But that is also one of the interesting things, because one of the let's say mitigations that we have applied, so maybe I'm talking about a couple of slides later, is to change a bit of placement and routing to improve, let's say, reliability, reliability overhead, to decrease the reliability overhead. But no, this result that I'm showing here, they are based on exactly the same bit stream. So bit stream is not regenerated for different FPGAs. So so this variation is definitely because of the either process variation or aging or this kind of thing. So it is like hardware variation, not software variation, I would say. But place and road variation is also some things that may have some impact into the at least reliability levels that we see here. And we used it for very likely in the placement stage. We have used it in one of the mitigation techniques, which I will talk later about that. Does that answer the question?
Yeah, your answer makes sense. So I think place and route problem is fixed because we have the same bit stream. We program every FPGA with the same bit stream. But I guess it goes back to this undisclosed details thing, where we don't even know if every FPGA physically gets programmed in the same place when we supply it the same bit stream. I guess this is something we don't know, or maybe I don't know. But place and route, I think, is not a problem for your approach.
Yeah, exactly. But it is possible to have like I think voltage aware place and route. This could be an interesting direction, actually. But for this study, which it is more like a understanding behavior, we looked into same place and route. But again, if we could somehow let's say consider voltage variation across different components into the place and route, because we have, of course, different type of net list, so they have different slags and different parts could be run in different voltage level, etc. So if such studies could be done, I think that's going to be interesting study. But yeah, we tried and this study to understand the existing, let's say, the behavior of the existing setup, but we did not look too much details, but of the place road. However, very briefly, we looked one of them, which I will talk later, but not that much. Let's say
okay. Let's not spoil it at this point. And well, maybe a final question is, before we move on too far from these slides, on YouTube, Obed, I hope I'm pronouncing his name right, Obed Mogaka asks if you provide the sources for this these experiments and this work online, and if they could use it in their research.
So you mean data? I mean, source code. I see it means, right?
Anything I think works, but source code results.
Yeah. Yeah, of course we have. So we have open sourced some raw data, I would say. It is in my GitHub page, and we have a lot of publications as well, and which in those publications we have discussed how to do that, and we are open to discuss these things and help actually to reproduce these results, but the source code of to do this experiments is not available yet online, but that's also possible. We would like to do to share it online. But I think that at this point it is probably feasible to do it more like in a kind of collaboration way. So if there's any idea around this, so we'd be happy to help to implement that one.
Okay, that's a really good thing. You have some data open sourced already, and you're open for collaboration. I found the repository, and I'm gonna link it to YouTube chat so people interested in this can take a look.
Yeah, that would be great. Thanks. Yeah. So is there any other comment or question here?
I think for now we don't.
Okay.
Anymore. For now.
Okay, let's move on then. Okay, so let's see how we move on. Okay, so I have just as a reminder. So we have seen this accuracy loss here. So next, I'm gonna talk how we can prevent this accuracy loss, which, as I mentioned, it's not good because this is like a lot of accuracy loss. It's a kind of collapse. So one of the typical techniques is frequency underscaling. So we run device in the previous slide, and this slide, we run device with the reduced voltage, but with the maximum frequencies that the device can work, right? So which I think it was like 333 megahertz for this implementation that we had, but we run them at that maximum frequency. One of the typical techniques to prevent actually the errors and also to prevent accuracy loss is frequency underscaling. So meaning that at the same time that we are reducing the supply voltage, we can reduce the frequency as well, which is a good technique because this can, so all the reliability issues are gone. Actually, we do not have any accuracy loss here. But what's happening is that we lose we may lose power actually. We may lose a bit of energy basically because by reducing the frequency, we of course increase the execution time, and this execution time will lead to increased energy consumption. So what's happening here? What we have done, one of the common techniques that one of the techniques that we have applied, it was reducing the frequency simultaneously with the supply voltage. So from 570 from this level, which is the minimum safe voltage level, so we have started reducing the frequency as well, along with reducing the voltage. So what we observe is that, and just again as a highlighting is that we do not have any reliability cost here, but what is the cost here is the cost of the basically energy. So we are losing the energy efficiency, as you can see here. So at this point, so we have almost 3% of the energy efficiency loss. But in terms of the power efficiency, it is better to actually, so in terms of the power efficiency, it is good to have it like to both reduce the power and voltage because both leads to reduced power. But in terms of the energy, it is better to not to reduce the frequency and keep everything in the highest level. This is a kind of trade-off. Again, it depending on what we want, what is the objective. So is it either power efficiency or energy efficiency? So we can decide to reduce the frequency and voltage below the nominal voltage, below the minimum safe voltage. If it is, if the goal is to actually to maximize the energy efficiency, it is better to not to reduce them. But if the goal is to maximize the power efficiency, so this result tells us that it is better to reduce both power and also both voltage and also the frequency. So this is one of the techniques that is applied to here as I said, to somehow get rid of the reliability, but of course it may have power costs, it may have, energy efficiency costs and performance costs, but it is good for power saving. So depending on what we need, we can decide to use this technique or not to use it. So, of course, it is. I mentioned that it is possible to integrate this technique with other techniques. So we have looked into quantization, for example. So this means that quantization is a technique that is applied in the application level. So meaning that the representation of the data could be less than could be variable, basically. It could be, in this case, we have tested 8-bit up to 4-bit of the data representation. So this is one of the potential let's say application, one of the actually very typical and very common popular application level power efficiency and performance improvement for machine learning. And we in this study we have looked into how it is correlated with the supply voltage level, basically with the supply voltage underscaling. And the results are shown here. So in terms of the energy efficiency, the behavior is very similar. So of course this is with a reduced with a reduced accurate, with a reduced quantization level, with a reduced bit levels. So we have, of course, better energy efficiency because we have less computations and we have less data movement. So we have better energy efficiency, and this trend, how it is going through undervolting, is almost similar for all of them with the same trend, but of course it's starting from different points, as I said, because lower data representation models is better for energy efficiency. However, in terms of the accuracy, it might be a bit of different, but not huge different. Actually, this is for just one of the workloads. I think that for studying for a big number of workloads, we may have a bit better slide, better results to discuss, but this shows that higher precisions are a bit more robust to the undervolting. So maybe not too much, but so the reduction for the 8-bit, for example, is a bit better than 4-bit. But this study again requires a bit more number of the workloads and also probably a higher number of the quantization levels, because this quantization level is a very narrow, is from 8-bit to 4-bit, is not that wide quantization level. We have done such a study, not for the undervolting type of errors, but for kind of random bit flips in machine learning, starting from 32-bit to 1-bit of the data representation model. It somehow confirmed these results, this term that I mentioned here, higher precision are more robust. But for complementing this study, I think that we need to repeat it for higher precisions, for 32-bit, 16-bit, etc., and also for more workload, actually. But the message of this slide is that so we have application level optimizations like quantization or pruning could be the same, and also we have a hardware level optimization, which it is in this case is undervolting, and it is possible actually to use both of them, to integrate both of them, and it works perfectly to achieve even better energy efficiency, which it is something that's achievable and is doable, basically. So for more information, I would like to refer for this paper published in DS in 2020. So we have discussed much more things, much more details about characterization as well as mitigation. We looked into the temperature as well, environmental temperature in this paper. So I would like to for more details, so there's a paper itself, also the talks, and also the slides are available here in this link, actually. Yeah, go ahead.
I have a question.
Yeah.
Can you go to the previous slide?
Yes.
So in the GOPS chart, the power efficiency chart, since you're not changing the frequency, why do higher voltage levels give more power efficiency?
So you say why
Yeah.
at the same quantization level, you mean?
Yeah. Let's say in the 4-bit, for the higher voltage you achieve 6 gigaoperation per watt, but in the lower voltage, for the lowest voltage you achieve, let's say 50 gigaoperation per watt. So is the frequency is the same, or like you
understand? Frequency is the same, but we are reducing voltage, right? So we're reducing voltage, so we have less power consumption. So less power consumption lead to better energy efficiency, right? So yeah, frequency is the same, but it is actually the same. So let me see. So by reducing power, by reducing voltage, sorry. So we are reducing power, of course. So yeah, probably this this should be like power, not gigaops per power, I think. Because so by reducing voltage, power should be for the same accuracy, power is getting improved. It's getting better actually. Sorry, it's getting reduced. I mean, power is getting reduced. So, but gigaops per power is getting should go up like this one. Yeah, should go up like gigaops per power. So yeah, I mean this charge. Yeah. So that is the one that is sure. I think it is this title is wrong. It is normalized power actually. I think so. It is a kind of normalized power, but gigaops per power goes up. It's getting improved, but power itself goes down. So this is a kind of normalized power consumption, I think.
Okay, I see.
Thanks for correcting, actually. Yeah. So yeah, any other question for this side before going to SRAMs?
Hi, Behzad. This is Nika here.
Yeah.
Based on the findings you had in this analysis, are there any recommendations for, let's say, FPGA hardware design or let's say more software stacks like place and route that would help the FPGA and execution on it be more resilient to voltage scaling? Are there some architectural recommendations that you could draw?
Yeah. I think that's a very good question. So this let me explain. Actually, I do not have a study about that, but there are some features that. So as you realize, this study is based on real devices, right? But this real device architecture for voltage, I believe that is not optimal. For instance, we have just a single voltage for all these components. So we have thousands or millions sometimes of routing resources, for example, and we have just a single voltage level for all of them. It's a bit different with the clock, for example. So we have clock regions, we have clock areas inside FPGA. So we have clock routing basically. But for voltage, it's not like that. If we change a voltage, all the components on the FPGA will be changed. So this is not optimal, I think. Of course, this is one optimization that I think that can be applied for the real devices. Of course, it requires a lot of study. I think what kind of voltage regions it is better to have, like how many of them, 4, 8, 16, or more flexible. I don't know. Also, probably, as I mentioned earlier, it is probably good to have like a voltage over place and route. So meaning that some nodes, some nets, let's say, of the FPGA in the net list, it is better to be routed in such a way that would, for example, if that certain net does not have that much slack, it is better to route it from the high voltage area, let's say. Why? Because we don't want to increase the delay, basically. So it is better to have such kind of optimizations at the software level, both, in software level, like place and route, also for the architecture level, I would say. So our goal in this study was actually exploring this kind of weaknesses, basically. So what we have observed is that both architecture of the real FPGAs and also the tools, place route, and also even higher level designing tools, they are completely unaware about what's happening in terms of the voltage. So they have very high level estimation of the underlying hardware, which is not really happening on the real system. So a very high level answer for your questions that, yeah, I think that there's a lot of things that can be done on the real devices to make them more efficient actually in terms of voltage, how to distribute the voltage across the FPGA, across the components. And even the other issues that we have observed is that there is not really standard. So we have different devices, they have different type of voltage distribution, voltage model, voltage, let's say, voltage distribution, etc. And also how to access to the voltage things. So we have such kind of, let's say, inefficiency, or I would say, it seems that the industry did not pay enough attention for these parameters, I would say, which it is very important for the power actually. So yeah, I believe that there's a lot of things both in architecture and software level that can be done for optimizations. And that was actually our goal, to study and first understand what's going to happen. And of course, next step, I think that is going to be how to improve this existing architectures, let's say. Does that
Thank you very much. Yeah, great, thanks.
Okay, cool. Okay, should we move forward at the back?
Yes, well, we have another question before we move on.
Yeah.
SB on YouTube is asking if it's possible that this undervolting will cause the device to operate near critical points more often, and leading to making it more sensitive to radiation and other hostile environmental effects.
Yeah, I think that's a perfect question actually. So at the end, what's happening is that I think that, yeah, it should have a correlation for sure, although we did not do a study, but it should have correlation, because at the end, radiation is a kind of transient energy, right? So this is an energy, particles of energy, which it is changing, let's say, the level of the robustness of the device. And if the device, my personal guess is that if the device is working in a reduced voltage, most probably this radiation will have faster, let's say, easier, let's say, very easily change the content of the, let's say, memory, if you're talking about the memory. So my guess is that the effect of the radiation in low voltage level is higher, but how much it is higher, I don't know, because this requires a study in real devices. But probably one direction of such study, or in that would be real devices, of course. So we use all the devices in like radiation machines, or what they call it, I don't know. But of course, there is simulation-based studies, another direction. If there's any kind of radiation simulation, let's say a circuit level, so we can integrate this with our study and we can see what exactly happening in such environments. But for sure, what I think is that these are not two independent parameters. Radiation and voltage, they are completely correlated.
Yeah, that makes sense.
Yeah, actually, not only radiation, there are many other parameters that could be affected. So like temperature, like any other things actually, which it is somehow affecting the hardware, the circuit. I think that in a low voltage, I guess, has higher impact, higher effect actually into the device. But we have studied some of them, but of course, additional study requires equipment, requires additional, let's say, tests, experiments, etc.
Yeah, I see there is room for improvement, and maybe the observations we can make if we have the proper setup and basically proper experimental setup, and we conduct those experiments. Yeah,
exactly. And even any kind of errors basically, which radiation, even temperature, high temperature, low temperature. So these are really something that would have effect into reduced voltage operations actually. Not just for FPGA, I think that in any device it is important, but of course in FPGA, the advantage that we have a bit more fine-grained access to the underlying hardware compared to GPUs and CPUs. So we can actually here program everything in a way that we want. So this is the advantage that we have started to do it in FPGA. So we can do this study more open than any other device, I guess.
Mm-hmm. I agree. Yeah.
Okay, cool.
We don't have any questions left.
Okay.
So we can move on maybe to the next
Okay,
paper or next word.
Okay, sure. Thanks. Yeah, this was the first part studied for internal components of FPGA, I would say. So we looked into the SRAMs as well, which are very important components of the FPGA. So I would explain first how they are floor planned on FPGA. So SRAMs are like located in FPGA in terms of blocks of SRAMs. So as you can see, this blue little boxes, they are representing a block of SRAM, which it is for usually 16 kilobit, which it is represented as like a matrix of the bitram of SRAM cells, like usually 18, 60, or 16 bit. If we add like ECC bits, they are 18 bits, but normally 16 bit. And we have like 1024 rows of them. So intersection of each of them represent a single bit cell. So data here can be stored as a 0 or 1. And we have thousands of them. They are like located in this way inside FPGA. So, and they are connected to a single voltage level, which it is very similar setup than the previous one that I showed before. So we have like a voltage regulator, and it is possible to regulate them and to monitor their content into different levels of the voltage. So this is more or less how we how SRAM blocks actually they are inside the FPGA, and we applied, we explored, we tried to understand the behavior of the undervolting for this component, because as I mentioned, they are very important. For example, for machine learning applications, usually SRAM blocks are exploited for storing for the weights or the biases of the neural network, which is very important because they are regularly, very frequently accessed, and this regular access, it may have if there's any error in even a single error, it may have a very huge impact on the accuracy of the neural network. So just as an example. So this is again, very high level. So just one other difference is that here the reliability, as I mentioned, so we discussed the power reliability trade-off. The reliability here is shown as a number of the bit flips. So we have written something, but we change the voltage and we may read a different thing. So this is something we call it bit flip. And we just counted a number of them in a different voltage level. And this is tested for a different set of devices because it was a bit earlier than the previous work. It was done in, I think, 2018 or 19. So the result has shown here for different devices, as you see here, for Zinc, for Vertex, and also for Kintex, for two identical samples of the Kintex, and also so we have totally 3 type of the devices. So the identical voltage, so all of these devices are fabricated in 28 nanometers, if I remember correctly, and the default voltage level is 1 volt, is shown here. So very similar to the previous one. So we have very large voltage guard band, meaning that we do not have any kind of bit flip. So all the data that we write, we read them correctly in the reduced voltage level. But below a threshold, which might be a bit different for different FPGAs because of the process variation that we discussed or aging, we start to see some errors in different blocks of SRAM. So just let me remind again. So we have different blocks. So errors are somehow distributed across different SRAMs. So we start to have, and this just shows only the number of the rate of them actually. So it shows only the rate of them. So we have like, for example, it increases exponentially until, let's say, 150 error per million, let's say. For this device, it goes to 250 per million. For this device, it goes 660, and this goes to 600. So they are comparable, although different devices have different amount of the memory, but since this is the rate, so it is comparable completely. So as you can see here, there's a lot of variation. Well, and at the end the devices start operating. So we have variation, different type of variation. First of all, the voltage level that the device start to have errors is a bit different for different devices, also start crashing. But I think the most important difference is variation is the rate of the faults, as you can see here. So we have, let's say, even 10 times difference between this and this, which, as we discussed earlier, and I think that's the same scenario that may happen here as well. So we had, this could be because of the process variation, or this could be because of the aging as well. Well, actually now I'm thinking is that it could be because of the place and route as well, because these are different devices and we generated different bit stream, of course, for all of them. But yeah, so we have very huge actually variation here. So, and also even for identical devices, as you can see here. So we have same identical device, we have even 3 times or even 4 times, 4 times difference between these two devices in terms of the reliability, count of the errors, which, as I said, it is due to the process variation or other parameters actually. So let's look at a bit more detail about how they are distributed, because this will help us to protect our application against these errors. So this chart only shows the rate of them, so just number of them, but it should be probably interesting to know a bit more detail of them, how they are distributed. For example, this shows how they are distributed. So what we observe is that the distribution is not uniform distribution. So it means that we have, let's say, thousands of errors and we have hundreds of block runs, and the thousands are not uniformly distributed through this hundreds of block runs. So we have a few percentage of them which are experiencing a huge number of the errors, which it is clustered here, as you can see. So we have like less than 2% of the block RAMs which are experiencing almost 90%, 85% of the error. So this means that we have like a very vulnerable block RAMs, and we have a very huge number, like 35% for this specific setup actually, which it is not experiencing any error actually. And this means that they are perfect. So they can run under very low voltage level. This is the lowest voltage level that we could run this device actually. So what does this mean is that we have, this actually shows another type of variation. So it shows the, they call it, I think, on-die variation or on-chip variation, things like that. So within-die variation. So this shows the within-die variation, and also very importantly, it shows the non-uniform distribution. And this numbers actually is very, I think, is very interesting, because it shows that not all the programs are faulty. So there are just a few percentage of them that are really faulty, and a lot of them that maybe are a bit faulty, or just they are not faulty at all. So which means that they are fabricated perfectly. So this will be very helpful for fault mitigation, which I will discuss in a few slides later. So maybe another characterization that we have done, and I think it is interesting to share it here, is the dependency for the data pattern actually. So what we'll observe is that the data pattern has a very huge impact on the number of the errors. So specifically, we observe that if the default data is 1, the logic of the 1, the probability that it will be flipped is much higher than if the data is 0. So as you can see here, for the data of written FFFF, so we have a huge number of the errors, but for 0, 0, almost 0, not exactly 0, but almost 0. So somehow the rate of the errors is dependent to the number of the 1 into the SRAMs actually. This is what we observed. And later on, actually, I have seen a publication, a paper, not from us, that have analyzed this in the spice level, in the circuit level, in the simulation level, and they show that why this is happening. Apparently, it is due to the architecture of a typical SRAM. So it is easier to flip from 1 to 0 than 0 to 1. So this has been proven actually somehow in the spice with some other people's publication actually. If necessary, I will share it later, actually. So there are other interesting results that I would like to share, and I'm sharing this characterization results because I believe that they would be useful for mitigation. So this is a property that we call them fault inclusion property. So this shows that if we have some errors at some certain locations, and if we continue reducing the voltage, those errors will never disappear. So we will have them. We may have some new errors in other locations, but we will for sure have those errors. And this means that errors are, as much as we reduce voltage, errors are kind of, let's say, stuck there. They are not completely stuck because, I mean, by the definition of the stuck at fault, these are not stuck at fault because if we increase the voltage, they may disappear, some of them. So they are not really stuck at fault, but with this definition that if you reduce the voltage, the same error will be at the same place. We can call them stuck at errors actually somehow. And this is with more quantitative numbers, as you can see here with the voltage reduction. This is showing a logarithmic scale for the certain devices. So this shows that just new errors happens and the previous errors, they are exactly in the same location and the same rate. And this is also interesting observation. And later I saw one paper, or maybe before this, that this technique, this observation or similar observation has been done for CPU caches, and they have used it for fault mitigation using ECC, which I think that it was published in ISCA. I don't remember the year. I think a bit earlier than this. So, so this is also summarizing actually all this characterization result that I've shown. We could generate a kind of map. Let's say we call them fault map. So this fault map represents actually how errors are distributed. And this is good to see because it is showing that there's not much, let's say, there's a little, let's say, geographical, let's say, dependency, but not that high because we have errors are distributed. And these maps can be used. So this shows the number of the errors for this certain voltage. So this is only for block RAMs, so we should exclude other components. By the way, this is like a exact physical location of the SRAM. So this is not, I mean, this is physical location, not the logical location, basically. And by reducing voltage, so the map changing a bit, as you can see. So at the end, with some higher level voltage, we have no errors. And this map is also very important because if we have this map for a certain FPGA, so this is something that our device, our software, let's say, placement and roads, let's say, which we discussed earlier, it can use these maps to somehow improve the place and road such a way that the critical nets will not be routed in this red area, or the critical data will not be located in the critical, in this, let's say, faulty components. So having this map as an input is very important and is can be very useful actually for the place and route tools. And this is what we have done actually, and then probably next slide I will show that. Yeah. So just before going to the next slide, I just would like to mention that this map can be completely different even for identical devices. So in the previous slide, we have discussed that. I've shown that the identical devices may have different rate of the faults, but this slide shows that the identical device may have completely different map as well, not only the rate, the map also could be completely different. So this means that this map is device dependent, so, not for even for the same model, we may have completely different. And how we use this as for improving the process software process, I mean, of the FPGA. So as I mentioned, we use this as an input for the placement stage. So it's a pretty actually initial implementation, and I'm sure that it's possible to have more advanced place and road, voltage eval place and road, but this was our initial implementation 3 years ago. So we input that map that I showed in the previous slide as an input for our placement stage. And this is, by the way, done on the real place road for the FPGA, for the Xilinx FPGA. And in the placement stage, we force our placer through some high-level commands. At the compile level, not in the runtime level. At the compile level, we force our placer to not to exploit those, let's say, those high vulnerable, we call them, or faulty, let's say, SRAMs. Why this works? And this works very good because it prevents a lot of errors and without too much performance. Why this is working? Because I showed earlier that the rate of the percentage of the block RAMs that are really bad, really faulty, is not high. It's just 2%. So what we do, we just extract those 2% and we tell the placer to not use them. So just wrote a different device, wrote a different components. This if this 2% was like 20%, potentially we could lose a lot of performance because we are let's say banning the placer to not to use some certain high percentage of components. But since we have just the 2% of them, and even less if we increase the voltage, so this is not impacting a lot into the performance. So we do not have really that much performance loss. I mean performance, I mean the clock frequency, the maximum clock frequency is not losing a lot with these limitations and without this limitation. But what we are gaining here is that we do not lose accuracy with reduced voltage level, which it is very good because with just little information and with just some compile time optimization, we could prevent a lot of accuracy loss for some benchmarks that's shown here. But of course, this has overhead. And what is the overhead? The overhead is that extracting this map is costly. So it requires some things to be done. Actually, we have a code that automatically can generate this. It is not that difficult. You can easily have this fault map. But the point is that it requires generated. It requires to do some compile time process. So we have pre-process, let's say, and then we create this, and then we feed the placer with this information. This is a bit additional process. So, which at this point is not quite that costly, but it may have a bit difficult for somebody who is programming FPGA, different FPGAs, or etc. But it is possible to embed it into, for example, one possibility is that to embed it into the flow, design flow, so some kind of fault variation map extraction or something like that, so that automatically tools can extract the map and then apply it to the process, apply it into the placement. But so far we have done it like manually. I mean, for different devices we apply it because this CAD flow that you see here is Xilinx CAD flow, and this is our flow actually. It's our additional things. So, but I think that is completely possible to embed somehow this process inside the Xilinx, let's say, design flow, which will simplify this process for the end users actually, without that much cost. But at the moment that I'm talking, it is possible to use another features of the SRAM. So SRAMs inside the FPGA, they are equipped with the ECC, error correction code, are very typical and very popular technique for fault mitigation in memories, and they have used it in SRAMs as well. So they are based on Hamming code. So they have 2 additional bits as a parity. So they have 16-bit for data and 2 additional bits for parity. And it has the type of single error correction and double error detection. So meaning that the error, a single bit error can be corrected and double error can be detected, but not corrected. So this is the existing ECC, and it is pretty optimal and efficient because they have used the kind of ASIC circuits for this implementation. So the overhead of ECC is not that high in terms of the power and performance. So it is okay to enable it, is what I'm saying. So we have enabled this and we have repeated our results, and the result was actually very nice because we have seen that most of the errors are gone. So as you can see here, without ECC, most of the errors, not all of them, they are gone. Why? Because we have observed that actually the most of the errors, undervolting errors, has the type of single bit errors. So and a few percentage of them are double bit. Actually, I have listed some numbers here. So more than 90% of the errors, they are single bit errors, and 7% are double bit, and just a few percentage are something that ECC cannot do anything. They are like more than 2-bit errors, which it is perfect match actually, right? So we have an ECC which is already implemented there. So FPGA have ECC in their SRAMs, and we have this undervolting error, which are usually in the type of single-bit errors. And so this ECC can take care of it without that much cost, again, because this is ASIC implementation. And of course, as expected, by implementing it for neural network, so this prevents a lot of accuracy loss, as you can see from red to green. So without ECC, we do not, with ECC, we somehow prevent the accuracy loss a lot because of the reason that I explained actually. So we have this also kind of mitigation in addition to the previous, like I would say, placement aware, voltage aware placement, and also earlier I talked about frequency scaling. This is also, I think, effective for undervolting errors. So we have this kind of such optimizations that can be applied for the aim of preventing reliability loss or accuracy loss for such reduced voltage operations in the FPGAs that we have tested. But of course, it is possible to apply many other techniques. There are a lot of error mitigation techniques like 3TMR, or even more specific, more customized version for these errors. I think it is possible to do. But we have so far tested these 3, and I think that somehow in 3 of them, we have observed good result, but of course with some trade-off. For the trade-off for the placement I mentioned, we need an additional process. For the frequency in underscaling, as I mentioned, we need a kind of, we may lose energy efficiency, and also for ECC, this maybe the only cost for here is that we need like 2 additional bits out of 18. So we have a kind of few percentage of additional area, let's say, which is kind of cost for this. So I think with this, I arrived to the end of the second part, and I would like for more information, take a look at our papers in 2018, mostly, micro and other one. If you have any question, I'll be happy to answer, I think, at this point.
Yes, thanks for the second part of your presentation, Behzad. So this idea is particularly interesting, I think, because you have exploited in one sense the error behavior in FPGAs to make, in a sense, the neural network models more resilient. Have you thought about other ways of doing that? I think one recent work, Eden, I'm not sure if you're aware of that, explores this in a different way. Maybe what they do is they have, similarly in DRAM, we can induce errors by operating it at like lower voltages, and then we can model the errors like you did. And then what Eden does is, as far as I understand, it injects these errors during the neural network's training,
Yes.
And makes the trained model more resilient towards errors, because the model in one sense knows where the errors and when the errors are gonna occur.
Yeah.
So maybe did you think about applying this to FPGAs, and would there be different challenges in maybe implementing it in this context?
Yeah, actually, that's a very good question, and I'm actually happy that you asked it, because what I was exactly thinking in that way, because one of the main process of the training is that is randomness, right? So we have an initial randomness, so the trainer can can work based on that random, let's say, behavior and improve some parameters, let's say, based on some optimization parameters. So and here we have like we have proposing such kind of randomness. We have done a work which was published, I think, in I don't remember the conference. It was FPL 19 or I don't really remember the conference. But we have done a training exactly in a way that you explained. So during the training, we were injecting these faults, and the faults that we were injecting, it was this raw data, raw errors that we have extracted from this study. And what we observed, as I remember, is that this is somehow adapting itself. So the errors, so that the trainer train itself based on this error. So when we do classification, somehow if we have the same errors, it's already there. So we do not see that much classification error. But the issue of that work was that we did not implement it on real FPGA. It was based on extracting raw data and applying into the software models of the neural network, TensorFlow and things like that. So which was a bit inaccurate, I would say. So I'm arguing my own paper. So which it was a bit inaccurate because the layout of the data, how you are putting data into the memory, it could be very important. But that work was not aware about that because we did not really have a memory. We just pretend that we have a memory, basically. So we just injected errors in some weights of the neural network, let's say. But yeah, those errors was real errors extracted from a real device, but those weighted, we did not know how they are actually stored, resided inside the memory. So I think that the better, what I want to say is that, yes, the idea that you are saying is completely feasible. At least the work that we have done shows that also that it is completely feasible, and it may have a lot of, let's say, advantage for preventing the reliability loss. But we have done it on a simulator, but not on the real FPGA. And I think that is also possible to do it on real FPGA. And I think that the most important reason that we have not do it was because of the lack of the tools. I think that, I don't know, these days, I did not really check the libraries these days, but in that moment that I was looking into, there was not many training algorithms implemented on FPGAs. So at least not much good tools available. But I think that these days should be a lot of them available, and it may be worse actually to do this study in the training as well. Yeah, but the idea that you explained is completely correct, and I think that would be a perfect idea to do the implementation.
Yeah, I guess you're right. Like if there was maybe some barriers to entry for this sort of work back then, maybe it's more mature now and we have more tools in this direction. But I think it would be somehow challenging if you wanted to do this, full system, end-to-end study on this FPGA system, because you would need to inject the errors appropriately, and that's seems challenging to me. I think I cannot think of an easy way of doing it.
Yeah,
maybe
exactly.
random errors might be more easy, but this also, and this sort of work, you have to, the error models are not fully random. You have to inject them at correct places.
Exactly. Actually, this is the most important difference, actually. So all this characterization things that I have shown, I was just trying to send this message that these are not random. So we do not have the random behavior in terms of the voltage. So these are following a certain behavior. So I have extracted this behavior. What kind of behavior could be this information? It could be data dependent, but when you are random is not data dependent, right? So it could be data dependent. It could be like, I mentioned a couple of them. It could be like a non-uniform distribution. It could be like fault inclusion, but these are not shown in a random data injection, random fault injection, basically. And I think that as a comparison case, injecting exactly the same way the random data is something that is could be good to show that, yeah, this random data is working in a bit different. I guess they should work in a bit different way, that how a bit more, let's say, this type of errors work. So, and also in terms of the tools, I just wanted to mention this point, that tools, there was really a big problem in that moment. I think, yeah, I even, the first neural network that I've implemented, it was using Verilog, and that was pretty terrible, actually. I spent a lot of time, this paper, I mean, this second paper that I've shown here. So I implemented a very small, actually, it was a very small neural network, but I used the Verilog to implement this model for this study, which is actually random error. This is the real error, this is the random error, actually. But yeah, that is, I think these days is much worse to like let's say, revisit the existing tools and reapply and this additional techniques that we discussed now, like different mitigation techniques, training, and all this thing. And I believe that that's going to be like a that may show some advantage as well, for sure. Yeah.
Yeah, sounds like a good direction now.
Yeah, exactly. And I think that even not even for convolutional neural network, and actually now we are discussing about the futures, but that's fine. So even for a different type of machine learning techniques, systems, models, and actually that this would be probably interesting, because at the end we are saving a lot of power, so it doesn't matter probably what kind of system is underlying, is what kind of workload it is, right? So, and of course, different applications may have different, let's say, different levels of the resilience, different levels of the power requirements, energy requirements, etc. These are all something that this type of work may enable, especially considering that now we have a lot of libraries that are available for FPGAs, etc. So yeah, definitely this is a very nice direction for sure. Yeah, training and also other applications.
Yeah, I guess we're focusing on neural networks a bit in these works, but as you said, it's applicable to many works that can benefit from, or that lie in the area of approximate computing, which is getting well, more populated, I would say. Yes.
Yeah, exactly. Yeah, exactly. This is a kind of, actually goes to the category of the approximate computing. At the end, we are paying some reliability cost to achieving some energy, right? This is probably in hardware level. So approximate computing probably covers a little much more bigger area, but we are in hardware level using the certain techniques for the certain application and certain devices. We are kind of doing some approximate computing evaluation or exploration here. So, but is this, as you mentioned, is this applicable and beneficial for other applications or not? Yeah, definitely it is. But how much it is the same amount of the power saving for other applications? Depends on the application. For example, for the database systems, since they cannot tolerate any kind of error, so even a single error probably it will be propagated into the outside of the machine learning. So in the convolutional network, it is not like that, right? So we have an error in the first layer. This error may not be observable in the output of the machine learning, right? But for database, it could most probably, I think, as far as I know, at least any error in any part of the database system, it is outside. So probably we are going to have a bit less power saving for database system as an example, but generally the concepts, the technique is for sure applicable. Yeah.
Sounds good. Yeah.
Okay, great. Any other question on this part, or should I move forward?
Yes, Behzad, I have another question.
Yeah, sure. Go ahead.
About the characterization results and the trends you've seen these SRAM devices on the FPGAs. What are the differences or similarities that you've observed in these SRAM devices compared to SRAM devices on other systems? Or what are additional constraints, or let's say relaxed constraints here?
Well, I have not personally done same study for other SRAM devices, but probably other people have done. And unfortunately, I didn't really look into those studies, but one thing that I remember is that somebody have done such a study for caches. And I think that they have observed a similar observation in terms of the fault inclusion property, this one, which I mentioned here. But the advantage that we have here for FPGA SRAM is that we have very fine-grained access to the data, right? We have like a bit-level access and also physical location, right? So we know exactly, for example, this certain bit, where is it located, and how it is accessible, etc. But in a cache, probably it's a bit difficult, and also in any other SRAM-based devices. But if you are talking about like SRAM chips, like ASIC SRAM chips, to be honest, I did not really look into. Most probably, I guess that should be similar. At least there should be a lot of similarities. But I did not really look into it. But in terms of compared to the SRAM-based CPU and GPU components, of course, the advantage that we have here is that we have much more fine-grained and more easy access to the device, to the SRAMs than the other CPU and GPU devices.
Yeah, it makes sense. Yeah, thank you very much. So I would assume that you can have more stronger mitigation techniques in this case.
Yeah, exactly. Yeah.
Okay. Thank you very much.
Yeah, thanks too.
Behzad, I have another question.
Okay, yeah, go ahead.
So these faults are read faults, right?
Yes, exactly. So we just do reading, yeah.
Did you observe any faults while writing?
Yeah, actually, I have done a lot of tests basically, and what I have showed in is the most, let's say, I would say something that are most probably, let's say, showable results, I would say. So I have done a lot of tests for the writing, to be honest, so write in a reduced voltage and read in a normal voltage, or in the other way, or both in low voltage level, etc. But for the writing errors, I did not observe any errors, but since I don't know why, so I did not really did much study, because I believe that it requires a bit more circuit level study. But what I have done before, I remember, is that I have done, we have tested like writing in a reduced voltage and read in a higher voltage level, and we saw that there is no error basically. So writing, the conclusion of that such system level study was that writing is much more robust than reading for SRAM at least. But why was like that? I really do not have, I didn't have that idea in that moment, and I did not continue looking into it. But I don't know, do you have any idea probably? Or did you see any paper?
Yeah, I guess not.
Yeah, but again, it is probably interesting. And also the reason that I did not really look into it, because the application that I have tested, it was inference. And in inference, we do not have any writing, right? So it's all data is already there. So we just read data. So we did not really need it to write something. So it was, everything was reading, but probably for the training that Ataberk mentioned as an idea for the future, I think that since the writing is a very important part of the application, it's really necessary to do such a study for writing as well, which I think that would be nice to do.
Yeah, that makes sense. And another question. Yeah, you said that I didn't observe any faults when I scaled the voltage up to the nominal one. So does that mean that these faults are coming from the sense amplifier, not the cells? Do you have any idea?
It is possible. Yeah, I think that is possibly it's coming from there. So it is not like a cell error. It's more like amplifier errors. But the problem is that since we do not have like a layout information for this SRAMs, it's a bit probably difficult to confirm what you said. But yeah, I personally guess that one as well. So, but I think that, as I mentioned, one probably way to confirm this observation is to make some assumption in terms of the layout and do some spice simulations to see these errors are really like SRAM errors or they're like sense amplifier errors. But I guess that, yeah, you're right. These errors are out of SRAM actually.
Yeah, that makes sense. Thanks.
Yeah, thank you.
I come back with another question, this
Okay,
time from the
ahead.
audience.
Yeah.
SB in YouTube chat is asking if the faults you're observing are only in memory or also in logic.
Well, these errors that I mentioned, well, one thing that probably I forgot to mention is that when we change the voltage of certain components, like SRAMs here, so all the other voltage in all the other components of the FPGA, they are working in a nominal level. So we do not change the voltage of any other component. So the only component that we change the voltage is SRAM here. But is this, but which so SRAM is a cell, as Ismail mentioned, and also some like additional, let's say, component around, like Sims amplifier and other things. So most probably this voltage that we are reducing, in this case is VCC VRAM, is connected to all those components around SRAM and around SRAM basically. But any other components like routing resources, like DSPs, like interfaces, like memory, everything is working in a normal voltage. So we try to make an isolation. Let's say, let me tell it in this way. But do we guarantee that this isolation is a perfect isolation? I cannot guarantee it because I don't know the layout of the device. But according to the datasheet of the producer, of the manufacturer of this device, this voltage level is feeding only SRAMs. But if they did something else magically and they did not share it, I don't know, because this is not something that I built. So this device is, we bought it, we get it, and we do it based on the datasheet. So yeah, we tried our best to make this isolation to make sure that the results are valid results. And among one of these, as I mentioned, is the isolation. So we have these certain components and we just change that voltage, nothing else. So I mentioned here 3 components, but when I change a certain components of the voltage, the voltage of the other components are all in nominal level, basically. So we tried our best to make this isolation, but it's a bit hard to confirm it, 100% confirmation.
Yeah, sorry. Yeah, thanks for clarifying this. I think this is a problem in every characterization work that deals with, well, existing chips of any sort.
Okay.
Even in DRAM studies, we don't know if we reduce voltage, for example, which components voltage reduce.
Yeah.
So this is I guess this is a problem that we'd have to deal with. But the good thing is, I guess your data makes sense and you make some assumptions and you have some hypotheses where you think that this errors are coming from SRAM cells, and it seems to make sense and it's backed up with data. And then the rest is we can hope that it's actually correct. But there's also there's always a possibility that these are not isolated, as you mentioned. Yes.
Yeah, exactly. Yeah, I agree with that. So I think that with this trend of open source hardware, well, actually it is not in the FPGA community, it's more like in processor community. But I think that this open source hardware, hopefully we will not have these issues for testing real hardware. So because we will have anything about hardware, hopefully, and then such studies would be much easier, I guess. Because,
I totally agree. Yes. Yes.
Okay, good. Any other question here?
Yeah, maybe another question, but a point. So you said that there is no right error, right? There is no right fault when we try to write SRAM. So I think that means that the logic around the SRAM, maybe inside the VRAM, is safe, because if we have faults in logic, embedded logic in the SRAM, in the VRAM, we should have seen this, let's say, faulty behavior when we write to. So I think it's pure, not that purely, but I think it's high chance that it's coming from the reading, just the reading, not the, let's say, embedded logic of the instruments.
Yeah, but I mean, yeah, it's possible, but I mean, so what I have done the test, probably we may need to increase this, improve this test, but writing in a low voltage level and reading in a high voltage level, somehow, if I remember correctly, disappears the error. So yeah, this means that probably the data is stored in the SRAM is correctly stored, right? Because we read it correctly, basically. So yeah, I think that somehow it's possible. Yeah, I mean, yeah, probably, but this requires a bit more study, because what I am saying is just something in my mind since 2 years ago. So probably it requires a bit more studies and more evaluation, experimenting at least.
Yeah. Thanks.
Okay. I don't think we have any other questions about this part of the talk.
Okay.
So maybe we can move on.
Okay, cool. Yeah, thanks a lot for the comment and questions, and please keep asking. I see. Okay, so we are now almost in the last part of the talk. So I mentioned about 3 parts, 3 components that we studied, and this is the last one, is high bandwidth memories. And actually, let me first give a very quick background now. High bandwidth memories. So they are kind of DRAM-based devices. They are stacked actually on top of each other, as you can see here. Why we have studied them? Because they are connected to FPGAs, some new versions of the devices in a bit faster and through some high bandwidth connections, like they call silicon interposer. And this is pretty cool because it provides a lot of bandwidth. As I mean, for the first version, if I remember correctly, theoretical bandwidth is around 600 gigabytes, but I think that HBM2 is even higher. And recently I've seen HBM3, probably it will come soon, or it's already out, I don't know. So we have very huge bandwidth here, which is very good for data intensive applications. So the data can be accessed through different stacks of the memory much fastly, because we have very huge bandwidth. This is what we have studied. So actually the reason that we did this study, because in the existing FPGAs, which was this one, I don't remember the model name, one from Xilinx. So the HBMs are connected to an isolated supply voltage. So we have discussed this isolation, supply voltage isolation, and the good part was that the supply voltage was isolated for this HBM. So we have a supply voltage for HBMs. So we did some study for exploring the HBM undervolting for that supply voltage. And this is a bit more detail how FPGA actually is connected to the FPGA for this certain board that we have tested. So we have 2 stacks of the FPGA of the HBM. So we call them left and right, 0 and 1. And each stack is connected to 16 channels of DRAMs, and each DRAM is 256 megabyte of the DRAM. So we have like a 16 here, 32 channels to access data. And actually this is where we can achieve the bandwidth. So if we could somehow get our results in parallel for all these channels, so we can get a lot of bandwidth. And this is possible actually if we could somehow, in our FPGA, which it is, as you can see, this SLRs representing FPGAs, like lookup tables, block RAMs, all these things. So if we could somehow put our application in such a way that can exploit this parallelism here, so we will have a very good bandwidth utilization here. So this is what we have done in our study, which was not targeted for let's say, maximizing bandwidth utilization. Our target was more understanding the voltage voltage effects into the reliability and power consumption of these components. So I have already mentioned about the benefits. They are much better energy per bit compared to DDR memories, but they are a lot of power hungry actually. This is the very important point as a motivation for our study. So they consumed a lot of power consumption. So our technique somehow, undervolting somehow could be good for improving their power efficiency. This is a very high level results that we have achieved, we have observed. You remember this green, yellow, and red, which is not shown here. So same definition, similar definition actually. So we have, so by the way, the nominal voltage set by the manufacturer for this certain devices, for this HBMs for this certain device is 1.2 volt. So what we observe is that for this device until almost 1 volt, we do not have any errors, basically. And we have tested it for different bandwidths. So from the maximum bandwidth we could achieve, like 300 megahertz, theoretically it is possible to achieve high, but this is what we could achieve in that moment, until much lower bandwidth levels. And we saw that the power efficiency is actually constantly, power consumption is constantly reducing through undervolting for all the bandwidth levels. So this means that so the power efficiency gains through undervolting is somehow bandwidth independent, basically. And you see the numbers here. So we have more than 50% power saving without any errors. We did not observe any errors into the HBM memories without any bit flip. Similar to the SRAMs here, we counted the number of the errors actually. And additional power savings through undervolting below the safe area. But here we have some errors. And we have actually looked into the behavior of these errors, which is shown here, some different stacks, as you can see here. So again, similar to the previous components, the rate of the fault increasing exponentially. So we have very huge increase in the error counts. So this is shown based on the number of the errorless cells in a stack for left and right stack, and also for the different type of the data. Here, unless the SRAMs, which we show most of the errors are 1 to 0 bit errors, bit flips. Here, it's not that much huge difference. We have a bit of difference, but the error, let's say, is not that huge. So a bit 0 to 1 errors are higher. The rate of the 0 to 1 bit errors are high, but it is not much bigger than the 1 to 0 bit error. So this is probably the architectural differences between SRAMs and DRAMs. So probably this is also interesting to discuss a bit. Let me put this here. Okay. So probably this is a bit. This is also interesting to discuss here. That what we observe is that below the voltage guard band, the power efficiency gain is a bit more significant. So as you can see here, so we have reduced power, and below this is the errorless part where we have some errors. So the power efficiency is a bit better, let's say. So we have much lower power. And why this is happening? I think that this is because we have some cells that are already stuck to 0 or 1, so they are not, they do not have activity, basically. Their content is not changing, so they do not have refresh, basically. So probably, so they do not consume much power. So probably this is the reason we have a bit better power saving below the voltage safe area, below the minimum safe voltage area, which means that we have some errors. And because their content is already stuck to either 0 or 1. Here shows a bit more characterization and map, similar map to what we have seen before, but here for stacks and also for the channels. This is the number of channels from 0 to 15. 16 is the channels we have for HBM 1 and 0, and also it shows the data dependency from 0 to 1 and for 1 to 0. So we have different type of variation here. I think the first one is the data dependency. As I mentioned, the 0 to 1 bit flips are a bit 20% higher than 1 to 0 bit flips. This is completely different behavior than SRAMs that we discussed in the previous part. The other variation is across HBM, so HBM stacks, I mean. So as I mentioned, in this device that we have tested, we have 2 devices, 2 stacks. Well, it was actually expectable because of the process variation and all the other root causes, I think, that we discussed before. So we have a bit more error in HBM1 compared to HBM0. And finally, the last variation is across channels, across pseudo channels. So each of these pseudo channels, if you remember, they are connected to 256 megabyte of DRAM memory, but they show completely different different percentage of the errors. By the way, these numbers showing percentage actually. So they show completely different percentage of the errors, as you can see here. This is, I think, again, understandable because of the same variation, process variation. And since we have the single device, aging is not the case here. So most probably it is because of the process variation errors. So, and finally, we have so far not tested yet a real application for this implementation, for this part, but it is possible to make a lot of trade-offs in terms of the rate of the faults that an application can tolerate, and also the amount of the memory is required by the application. So this based on what application needs in terms of the amount of the memory and how much is its resilience level, it is possible to make a lot of trade-offs here to achieve power saving, basically. For example, if an application cannot tolerate any error, for example, so everything should be perfect in terms of the error. So, and it requires all the memory channels, 32 channels of the memory. So the minimum voltage level that we can set is 0.98. So we cannot set lower than that. But if our application can tolerate 50% of the errors, then we can, and it requires 32 channels of the memory, we can reduce more, and so on. So we have a very nice trade-off here, but this trade-off for real applications, we have not so far studied yet, although we have some ongoing works on this, actually. That was last slide for this part, and I would like to refer for further information for this paper published in date last year. And of course, any question now or later is also welcome to be answered. Ataberk, do you have any comment or question here?
Yeah, thank you for your talk so far. We do have questions. I think Nika has a question.
Oh yeah. I was actually thinking maybe I can ask it at the ending part, but maybe now that you brought it up, I can ask right now. So I was wondering, with these three directions that you've explored, and also the potential work that can be built on top of it, how far do you think should we go to kind of like close the gap, or like make the gap smaller between power efficiency of ASIC and FPGA?
Okay. I think that this maybe a higher level discussion, this exploration, the advantage of this exploration and this study is that it does not really require any heavy hardware or software modifications. So with a minimal modification on the hardware and the software means it could be an application, or it could be like a design flow, CAD flow, design automation flow, actually. So with a minimal optimization, we can achieve a lot of power, which we have shown like 3x power. 3x power with a minimal modification, I think it's a very good number. But does
So my question was that mostly in the direction of like, would these changes or like maybe extreme versions of them make FPGAs kind of like power efficient, such that in some cases they will be able to take place of ASICs in some resource constrained environments?
I got the question. I was going to say this note that this may not bridge that gap. So
I see.
That this will not bridge that gap, so that FPGA would be more power efficient than ASICs. But considering that we have like a minimal modification, I think that's a good number, because considering the other advantages that FPGAs have compared to ASICs, that's fine, because we have reconfigurability here, which in ASICs we do not have. But this makes FPGA more energy efficient than ASICs? No, I don't think so. This is not possible, because we have a lot of reconfigurability here. We have a lot of unnecessary let's say components if we want to just run a certain application into the FPGAs. So the short answer for this question is that no, this is not going to like a bridge, so make FPGAs better than ASICs in terms of power consumption, but this is going to make FPGAs better than previous FPGAs with the minimal modifications.
Yeah, makes sense. Yeah, great. And one other question. So in these three parts that you've explored, do you think that makes sense to have a holistic study, or do you expect that these three parts would have interactions with each other?
Yeah, I think that's a very nice question. And the reason that I have shown it as a tree independent part, because it has done in a tree independent time. So it started with my PhD, like second time of my PhD, and later on continued as a later on. So we have done it through all the time. So, but of course, it's a more like holistic, integrated way. It is for sure. So imagine that we have a system which has all these components. It has even more components actually. So yeah, that is definitely an approach and to save power in all these components. But one thing that is possible is the interaction between all these components and the correlation between these components. Because as I mentioned, when I was talking about the third part, for example, of HBM, so the voltage of the other component was in the nominal level. Or when I was talking about the SRAMs, voltage of the other component was in nominal level. But the question is that what happens if we reduce them all? So this may lead to some even more, to some like probably hard to explain behavior in terms of the reliability. So, but this was, I think, some exploration for sure. And I think that in the future, that's definitely a very approach to go actually.
Thanks. And one final question for this stage. Have you found any correlation between like features of different modules or like logical components that are being implemented on the FPGA with their resiliency towards voltage scaling? So you explained already some application dependent features, but I'm wondering, let's say from architecture perspective, if we look at, let's say an RTL based circuit, can we infer how resilient it will be for these scalings?
Yeah, definitely. I think that's there might be a bit of difference, but for sure, as Ataberk also mentioned, it is possible to it is possible to do many things actually, to like model these things into RTL models, to model this real result into RTL models, or to repeat some let's say SPICE studies, simulations into RTL models of SRAMs or DRAMs. But again, the one main question that remains here, I don't know how big is that question, is that are we comparing orange and apple, or this comparison is a correct comparison? Because we, as a user of the FPGA, we do not know the layout of the device, right? Or any other system, CPU, GPU, etc. So, but if we have an RTL, if we could get access to an RTL of that, let's say FPGA, whatever, I mean, FPGA or its components, that comparison could be fine. But since we do not have that level of the information, probably that comparison will not be like 100% accurate, but maybe it may worse to do some such comparison and study. So yeah, the answer is that yeah, definitely that is possible, and actually one of the ongoing works that we are doing is that one, but we still do not have like a result to see how much comparable and how much fair is this comparison between the voltage underscaling in RTL level of a device, which is SRAM, the cop table, DSPs or whatever, and a real system like FPGA inside FPGA. So we still have a bit like question for that part.
I see. Yeah, that's definitely an interesting direction. Yeah. Thanks a lot. Thanks.
Yeah, thank you too. Yeah. So the work should be.
Maybe I have a very small question.
Yeah.
So I see that you in the study undervolted HBMs and basically looked at bit flips across the whole HBM chip. And there was a similar study by Safari, or earlier study, I think, called Voltron, where we did a similar, where we ran similar experiments. I was wondering if there were any, like, if the results are conflicting each other, or if there's some similarities, and if there are differences, what do you attribute those to?
Yeah. I think that's a very good question. Although we did not do like a detailed comparison, I think that work, it was probably on DDR3 or maybe DDR4, I don't remember. But for sure, I expect a lot of similarities with the work that we have done here on FPGA, on HBMs. Because at the end, this is also a DDR memory, so DRAM-based memory. But yeah, I think that but we did not really do like a one-by-one comparison in terms of the characterization or rate of the faults, etc. But one point here I would like to mention is that is the difference between two types of these studies, which makes comparison a bit probably difficult, is that here we are not able to test many devices, many HBMs, because HBMs are like a package with the FPGA. So here, as I mentioned, we just tested a single device, but in DRAM, it is possible to test hundreds or thousands of devices, right? Because it's just a DIMM, right? But here it is not a DIMM, it is a board. Basically. It's like a very expensive board, actually. This board that is like, I think it's more than 10,000 at that point. So accessing to a lot of them and repeating this study and making comparison with more like a 2D DRAMs, it requires a lot of equipment, at least I would say. But for studying this level that we have done for a small number of the devices, I think that there's a lot of similarities in terms of at least the data pattern dependency, although I did not do like a very detailed comparison in this paper. But for sure, since they are both DRAM-based devices, I guess that, and I think that they have a lot of similarities, yeah, in terms of the rate and also in terms of the location, etc. Yeah.
Yeah, what you say makes sense. I think I agree with the where you said it's really expensive to scale up the experiments on HBM chips because they come with boards. Usually one device comes with a board and it's expensive to do.
I think that hopefully with a bit better setups, or in a soon or late, I don't know, when more devices with HBMs are available, probably it would be easier to do scale up. And as much as also FPGAs are getting more popular, I think that, as I mentioned, in the data centers, they are getting more popular. It is also easier. It makes easier to complement and to scale up such studies as well. So I mean that future will solve some of these problems actually.
Yeah, sounds reasonable.
Okay. So any other comments or feedback here? Question?
I don't see anything new in YouTube. Okay. I think Zoom people also ask their questions.
Okay, cool, thanks. So actually this brings me to the end of my presentation before going to the discussing on the future works, which we actually, interestingly, we discussed many of them. So most probably will not spend much time on that. But let me just summarize again and review again what we presented today. So we have started with this motivation that merging applications, they require a lot of power, and because they have a lot of data, and FPGAs could solve some of these problems because they are very good in terms of the reconfigurability, in terms of the parallelism, and in terms of the pipelining. But of course, also in terms of the flexibility compared to ASICs, but their power efficiency is a problem compared to the ASICs. And we proposed and explored exploiting supply voltage underscaling on real devices for different components of the FPGA. We have done several kind of characterization in terms of reliability, power, workload characterization, process variation characterization, several mitigation techniques applied in several applications. Some made some changes into the FPGA's CAD flow, and also we have studied several type of devices, several components like lookup tables, SRAMs, and HBMs. Among the main results, it was notable to achieving more than 3 times our power saving, and without any which most of it is without any cost, but there are some part of it with cost of the reliability. And for this reliability part, we have proposed some techniques for the machine learning devices, machine learning applications. But does this end the study? Yeah, of course not. This was what we have done. It was basically the first work, as far as I know in that moment, that have done such study on real devices. But we are not done yet, and I think that it's possible to repeat such a study for many different, or expand such a study for many different devices and to achieve and gain more energy, which I listed some of them here. And I think that we have already discussed many of them, but I would like to very quickly mention them. And I think that a very important, let's say, limitations that we have in such a study is the availability of the device, which FPGAs, as I mentioned, first of all, not all the FPGAs have voltage underscaling capability. And also, so we have just some brands of the FPGAs, some models of the FPGAs, some families of the FPGAs that's possible to do to apply voltage underscaling. This is a big limitation. Also, the other limitations that we have is that different FPGAs have different voltage underscaling capability. So, and also different setup. For example, for some FPGAs, I have seen that for some families that SRAMs, block RAMs is not possible to do underscale in terms of the voltage. So we have a kind of very heterogeneous and let's say unpredictable voltage architecture for the FPGA. So this is a bit I don't know, confusing in terms of for somehow make this work let's say on any FPGA, let's say. But still it is possible. So we have shown that on several devices that is possible, that is doable, that is feasible work and with some good efficiency. But of course, it's possible to extend it for different technology nodes, for different architecture. We have done several characterization, but I think that more characterizations is possible. And for especially more mitigation techniques is possible to be done. Like we have tested several of them, but other technique, checkpointing, rerunning the application, etc. These are possible. So I mentioned several variability, but other variability could be studied, aging, radiation, temperature, etc. This is, I think, one of the optimizations that can be done on real FPGA. I mentioned it earlier, I think. So we do not really have voltage domains, and also supply voltage rays are pretty coarse grain. Sorry, they're very fine grain. So this means that, so we have just a single line of the voltage, which is feeding all the, let's say, HBM data. But probably it is better to have like a per stack voltage, or I don't know, per something. I mean, it's a bit more fine grain voltage, let's say, distribution. At least to do some research study that's worth to do it, but we do not have it at this point. Or for FPGA components. So for example, we have some components that in FPGA that we have tested. We have some components that they're sharing a single voltage. Like, for example, if I want to make an example, routing resources and DSPs, they're sharing a single voltage, which it is not good idea, I think, because look, routing resources and DSPs may have different reliability thresholds for certain applications. So probably it is better to run them in a different levels of the voltage. But now at the moment it's not possible because we have just single voltage goes to both of these components in common, which is not probably optimal. So we have such kind of optimization that is possible to apply for devices, but this needs to be done, I think. So of course, it is possible to, let's say, as I mentioned, the advantage that we have in FPGAs is that they are quite, let's say, programmable. So this allows us to study a lot of things compared to the CPUs and GPUs. But one potential direction and optimization is to somehow emulate this study into the processor simulators or GPU simulators, because we extract data from the real device and we could apply for the CPUs or GPUs, or any other device, because it's not possible to do the same study on the CPU. Most of the times it's not possible. Or any other device, or any other, as mentioned, at the data center, etc. So, but I think that there is a lot of things possible to do as a extension for this study, and we are already doing it. And I think that I'll be happy to get any further feedback offline or later through email. So feel free to contact me for any comment, question, suggestion, or criticizing, or even anything actually related to it. It's appreciated. So I just want to, I think this is my last slide, but I would like to mention one point before ending officially. So I would like to mention to the limitations again, so that real devices have, and this makes a lot of let's say issues. For instance, even different manufacturers, they have different considerations in terms of the voltage. So we have two major FPGA manufacturers. The other manufacturers that we did not test, they have very different voltage distribution model, which it is very different with the brand, with the manufacturer that we have tested. So they have like voltage ID, for example, they call it, which it is like a bit, let's say, process variation aware voltage. So meaning that not all the device that you can get from that family has a certain voltage. So each device has a different voltage because through the process, through the fabrication process. So probably they do test and they put the different voltage for that. So we have this kind of optimizations, but the point is that there is no standard. So there is no model that is reliable model, let's say, which everybody can use it. Or even for a certain manufacturer, different models, different families, they have different voltage distribution. Or some FPGA families, they do not have any voltage capability. So these are all limitations, which I think that somehow limits these very important parameters compared to the other similar parameters, which is clock. So we have spent a lot of energy in both research and industry on the clock distribution, but I do not, to be honest, see that much effort into the voltage. And I think that I hope that this work that we have done in real FPGA, this can somehow motivate and open some discussions around this topic and make the next generation of the FPGA more voltage aware, I would say, and more energy efficient. And we are also, from our side, also we are also spending a lot of time and effort on that. And as I mentioned, we'll be happy to discuss further about this topic and also ongoing and future work. So with this, I think that I arrived to the end of the talk already, I think more than 3 hours. So I would like to thanks for attention from the Zoom, as well as for the YouTube, as well as for the offline watching, somebody who's watching this offline. So I appreciate all your time and thanks a lot for your attention. As I mentioned, for any comment or question, you can contact me through these means. So I would like to get back to Atabak for anything remains. Okay.
Yeah, I have one question.
Yeah, for sure.
So you presented interesting pointers to future work in the last slide.
Thanks.
One thing I had in mind, I don't know if you, well, clearly, I mean, you don't list it here, but maybe you've thought about it. This errors that you observe are obviously beneficial when we exploit them for approximate workloads, when we reduce voltage and then we save power. But the errors themselves could also be used through random number generation, for example, or physical unclonable functions, depending on the behavior of those errors. Have you thought about that at all, or could you like give give us your thoughts about that?
Yeah, definitely. That's a very good point, actually. So this presentation and basically this work, all the publications that we have around it, it has a focus on power, energy, performance, and reliability, of course. But as you mentioned, security is very important thing here, because at the end we are changing some value somewhere without actually with some settings, right? And this may, well, it can have like security problems, but as you mentioned, one good part is that it can be used for some random, because we have some kind of random, as I mentioned, this random different devices, they show completely different behavior. So this means that each device has a key, kind of key, because that's the variation map that I've shown. This is a kind of ID for that device, right? So that ID for different device, even for identical brand, identical family, is completely different. So what you are saying is completely correct, and I think that we are working on that. Is one of the ongoing directions in this study. And we already have some results, but I would like to leave it for the future, because it is under review work. So probably it is better to have it like a final version of the results, final version of the study, and then we can share it for public for sure. But of course, as I mentioned, this is not even limited to the random number. That's a lot of things that can be exploited for this error type of the errors. Security for sure is one of them, for sure. This is, and even if I remember correctly, just correct me, the correlation of this error, voltage errors, with other type of errors like row hammer, it has been studied recently by Safari, and this is also very interesting. I think like a correlation, let's say. And of course, any type of the errors is also correlation with them is also can be studied, like radiation, for example, is one potential things. So yeah, short answer for this question is that yeah, definitely random number generation is a very valid direction, because any device has its own ID in terms of the errors. We have some error, we have some results, and most hopefully very soon they will be public for everyone.
Yeah, that sounds reasonable, not to disclose everything about an under review paper.
Yeah.
What you say also makes sense. So yeah, thank you for answering that.
Thanks a lot.
And then the paper you talked about, I think the work that we were doing recently, relating row hammer to voltage. Yes, in DRAM. It's called Hammer Dimmer. It will be published on DSN this year. It's actually, I think in this month, we will have the paper published, so people can check that out. I can send a link. Well, I cannot send a link probably to the publication because it's not there yet, but I can send the name of the paper to chat. And there is another question in YouTube chat. Maybe this is taking us back a bit, but SB is asking, what effects does lower voltage have on the current related losses? Maybe this is referring to voltage drops, or even I've heard the term voltage droop at some point. Do you have any thoughts on that, or have you investigated that maybe?
Well, no, not really, because this, I think that this requires a bit equipment, I guess. We did not really study that one, but I personally think that most of these errors are probably that's the root cause. We have, I don't know, IR drop, you said, so I believe in you. So probably that is the root cause, but how much is that? We did not do experiment because of the equipment, actually, I think. But for sure, it has effect on that, yeah.
Maybe IR drop also is like a well, symptom of the undervolting, not the actual cause, but maybe, I don't know, I'm just making it up at this point.
Yeah, but I think that that's valuable to do such study, but in a bit more laboratory equipment. But we have done all this study in a room in our group, so I think that in the laboratory equipment that is possible to do such studies as well, for sure.
Yeah. Okay, there's no other questions on YouTube. Okay. Do we have anything else on Zoom? I think we can take that as a no.
Okay.
And I guess you're done with the slides?
Yes, I'm done.
Okay, Thank you so much, Behzad, for the very informative and insightful talk. I think it was like people enjoyed it, watching it, I think, because we have many questions on YouTube also. I guess we can end the live stream soon.
Okay.
And hope to see everyone in the next Safari Live seminar.
Okay. Thank you so much, you and everybody else in YouTube and Zoom.
Goodbye, everyone.
Bye.